In the vast emptiness of space, every star sings its own song, not in sound, but in light. Each glimmering ray carries a hidden pattern, a sequence of colors and gaps, a cosmic barcode known as the atomic spectrum. It's through these spectral lines that we've learned what stars are made of, what distant galaxies are burning, and even how fast the universe is expanding. But behind this simple play of light lies one of the most profound discoveries in all of science, the quantum nature of matter itself. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. The story begins in the early 19th century. Scientists like Joseph von Fraunhofer, a Bavarian optician, peered through a prism and saw something unexpected. Instead of a smooth rainbow from sunlight, he noticed hundreds of dark lines slicing through the spectrum. These became known as Fraunhofer lines, mysterious gaps that hinted at something hidden within the light itself. Later, when scientists passed light through hot gases, they found bright lines, each element glowing with its own fingerprint of color. Sodium produced a brilliant yellow doublet, hydrogen, a vivid red and blue-green, mercury, bright violet. It was as though nature had assigned every atom a unique color code, invisible until excited by energy. This marked the dawn of spectroscopy, the science of studying how light interacts with matter. At the time, the atom was still a mystery. Scientists imagined it as a tiny, indivisible sphere, a miniature billiard ball of matter. But the strange patterns of the atomic spectra didn't fit that picture. Why would hydrogen, the simplest of all elements, emit only a few specific wavelengths of light instead of a continuous rainbow? This question haunted physicists, and in 1885, Johann Balmer, a Swiss schoolteacher, found a mathematical formula that described hydrogen's visible lines with astonishing precision. But he couldn't explain why it worked. The mystery deepened until a young Danish physicist, Niels Bohr, entered the scene. In 1913, Bohr proposed something revolutionary. Electrons don't orbit the nucleus randomly like planets. They exist in quantized energy levels, precise orbits where their energy is fixed. When an electron jumps from a higher orbit to a lower one, it emits a photon, a packet of light, whose energy corresponds exactly to the difference between those two levels. This idea explained why atoms only emit certain wavelengths. Each line in the atomic spectrum represents an electron's leap, a quantum transition. For hydrogen, this became known as the Balmer series, corresponding to electrons falling to the second energy level. Other series, the Lyman and Paschen, were found in the ultraviolet and infrared regions. The atom was no longer a miniature solar system. It was a quantum machine, emitting light in discrete, predictable steps. As spectroscopy advanced, scientists built detailed spectral catalogs for every known element. Each spectrum became a fingerprint, allowing us to identify substances even from light years away. When astronomers turned their spectroscopes toward the sun, they were astonished to find patterns identical to those produced by hydrogen, helium, calcium, and iron on Earth. In fact, helium, the second most abundant element in the universe, was discovered in the sun's spectrum before it was ever found on Earth. Spectroscopy had become the universal language of atoms and the key to decoding the cosmos. But even Bohr's model wasn't the full story. As spectrometers grew more precise, tiny splittings in spectral lines began to appear, patterns too fine for Bohr's simple orbits to explain. Enter quantum mechanics. Physicists like Erwin Schrödinger and Werner Heisenberg revealed that electrons don't travel in fixed paths. They exist as probability clouds, described by wave functions. The energy levels of atoms are shaped not just by distance from the nucleus, but by angular momentum, spin, and magnetic interactions. These subtle effects, known as fine structure and hyperfine structure, give rise to the intricate beauty of modern spectra, allowing scientists to probe atoms with almost unimaginable precision. Today, Even the smallest shifts in spectral lines, called Doppler shifts, let astronomers measure the motion of galaxies, the spin of exoplanets, and the expansion rate of the universe itself. The science of atomic spectra has evolved into powerful tools that shape modern life. In medicine, spectral analysis forms the foundation of MRI and PET imaging. In chemistry, it enables laser spectroscopy, revealing molecular structures and reaction pathways. In astronomy, it identifies the chemical makeup of stars billions of light-years away. Every pixel of a galaxy image, every glow from a nebula, carries within it the whisper of atomic transitions. Even quantum computers and atomic clocks, the most precise instruments ever built, rely on the stability of atomic spectral lines to keep time and encode information. The spectrum isn't just a display of color. It's the blueprint of the quantum world. So the next time you see light passing through a prism, remember, you're looking at the handwriting of the universe. Every color, every gap, every flicker is a direct signature of the quantum dance within atoms. From the faint glow of distant galaxies to the fluorescent lights above us, all are connected through these same atomic codes. In the end, the story of atomic spectra is the story of how light revealed the invisible, how a rainbow became a revelation, because when we decode light, we decode the universe itself. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about the science of atomic spectra and its contribution to modern technology. Join me next time for another deep dive into the strange and unusual world of quantum physics.